was so quick in the setup. It's always suspicious. Something. I might have forgotten something. Okay, before we officially move on, I wanted to briefly come back to this proof from yesterday. Specifically here, the lower bound for selection. There we go, no pen. No, that's better. Specifically here, this lower bound with the adversary. I think I confused myself successfully yesterday in saying this would also work against a randomized algorithm, but that's not true. I mean, the statement is true. You can prove that 1.5 comparisons in expectation are necessary even for a randomized algorithm, but this proof wouldn't show it. And the reason is that we're kind of we're cheating in that we modify the input while the algorithm is running. And for a randomized algorithm, you can't do that. So you should, for a deterministic algorithm, you should think of a comparison tree, like you use it for showing the sorting lower bound. An algorithm that's comparison-based, we don't care what it does in between, but it will at some point ask a comparison question, and then we have to answer. Now, a deterministic algorithm is one such tree, and the branches of the tree depend on the outcomes of the comparisons. So it might do different things in different branches, but it has to have a leaf for every possible input. And there the input is kind of fixed. What we're doing with this adversary here is we delay the decision which leaf will eventually reach in the process by saying we make the outcome of the comparisons that the algorithm asks us to answer depend on some past behavior of the algorithm or what we know about the elements so far. And you can imagine that as navigating down the comparison tree. But the thing is, you're effectively modifying the input while the algorithm is running, which means all you show is that there is one input where the algorithm needs to do these 1.5n comparisons that we argued. But it could, in principle, be a single input. And a randomized algorithm might just average those high costs away by doing much better on all the other inputs. And so you need an entirely different technique and setup to prove this randomized lower bound. Maybe if we have time, we'll come to some techniques for proving lower bounds against randomized algorithms. There's some cool and interesting tricks there too. But I just wanted to kind of clarify that the confusion there was that the adversary keeps modifying the input, which you can't actually do. It's kind of once the algorithm runs, the input has to be fixed. The trick here is that we don't decide which input we look at until later, which is fine for a deterministic algorithm where we just want to show there is one hard input. All right. And then, as I said, you can improve this adversary to be more cunning, and then you get this 2n upper bound, whereas we can get a lower bound and you get an upper bound of 1.5n with randomization. So in this problem of selection by rank, deterministic algorithms are strictly less powerful. Right, but now to something else. That's the part where we should officially start. So before we continue the discussion of actual randomized algorithms, I'd like to take a step back and for one, it's kind of 2 steps back. I'd like to properly define what it means if a randomized algorithm runs and has a certain running time in the where the possibility is that it doesn't ever finish. This is something we'll be confronted with, and we'll have to find some proper solutions for that. And properly handle randomization in general and this particular problem in particular, we'll need some background from probability theory. Much of this will be repetition from some kind of, most computer science curricula have some probability theory in them. They may differ in how formal they get. And so most of it will be repetition. I didn't want to include more than necessary, but really there was this one bit where we need a little bit of a more abstract view on probabilities. Okay, so without further ado, we'll revisit some key terms, also to make sure the terminology is known to everyone, also the English terms, and have a place to look up notation. As always in computer science, we'll mostly deal with discrete things, but it turns out we can't fully avoid continuous or more general probability spaces. And sometimes continuous is just a convenient way to analyze things, even if the underlying process is discrete. So what's this all about? If you want to formally speak about probabilities and what does it mean that something is random, and how can you quantitatively make statements about it? The first thing is you want to settle for some framework where you can assign things a probability. And that's what a probability space is about. The easiest case is the discrete case. You have some ground set. These are the things that can happen at the basic level. Let's do a concrete example. A fair die, standard 6-sided die, no fancy role play things. Then the possible outcomes are just the number of, let me draw it like a graphical way just to make sure that these are effectively arbitrary objects, and that's not a nice 5. So let's represent these as like abstract symbols. We're also in the city of the blind, so it's almost looks like Braille, but of course it's not because it's 3 columns. But okay, just some abstract objects. I guess I should have drawn some shapes around this to make it even nicer. So this is the different sides that a 6-sided die, a cube, can come up with. That's the underlying event space, or do we have a name for omega? Does anyone know? It's just the basic events, I think. Well, that's the one thing. So you have to say in a random process, what is the possible things that can happen? And then the second important bit is we have to assign them probabilities. That's the whole purpose of this. And so I'll always denote probability by this double stroke blackboard font P, just to have it a little shorter than spelling out probability or something like that. In principle, this is just a function. In the discrete case, it maps subsets of our ground set to probabilities. But really, it's determined by giving the individual elementary events some probability weight. And so here, in the case of our fair die, we would say the probability of each of those is just 1/6, if it's a fair one. Okay, I already regret drawing this in different colors. Just as one example, and of course you can, in this case, let's define it for all of the faces to be 1/6. That's a fair die, but you could also have a kind of cheating die where maybe the 6 comes up more often. Once we defined for the elementaries outcomes what the probability is, you just sum up. If you have a larger set, in the general case, we have a set of these, and you just sum up the weights. That's super boring and trivial, right? So the reason why I spelled this out is to contrast it to the general case. not everything is discrete. Now here already things are not necessarily finite. My example with the die was finite. Omega is a fixed size, but it could be a countably infinite set. That's all right. But we would still call this discrete because you can bijectively map it to natural numbers. That's what countable means. But that's not all there is. If you want to talk about real numbers, then trouble already starts brewing. And while we're at it, we'll actually need it slightly more general. So again, like a kind of normally for much of statistics and what you do with normal data science things, it's fine to stick to discrete or real valued continuous random variables with some density or so. There's one point where we need to go beyond that. So in the most general setting, a probability space has the following minimal requirements. Again, omega is some set of, okay, I called it points here, so elementary events, the things that can happen. And then we have to speak about more carefully, we can't do all subsets if omega is a continuum. So instead, we'll take what is called a sigma algebra, which is just a collection of sets with some properties. So these are all sets over omega. In the discrete case, just take the power set, but in general, you want a restricted set. We always need that the empty set is in there, and then we want that it satisfies closure properties. So whenever some set is in this set F, then we want that the complement set is in F, and any countable union of sets in F is also in F. So you can reason about what this kind of structure looks like, and that's the topic for a measure theory class that I'm not so interested in, so we'll just steal the results and don't worry about why they're true. What people might have heard of is the Borel sigma algebra. This is the solution for this problem in the continuous real case. If you have, say, omega all of the real numbers, or the real numbers between 0 and 1, then you can basically solve this, this question of what kind of elements can I look at, or what kind of sets of real numbers can I sensibly look at, by taking all the intervals, say the open intervals from some number a to b, and the closure under all these operations. And that turns out to be a well-defined sigma algebra. It has a name, and you can define probabilities on them. Why the whole thing? Well, in general, there's sets where you can show you cannot sensibly define a probability by designing them in a mean way. Again, this part of the theory is not relevant for us. So that's just listing the minimal requirements, and we'll be happy with those. Then the second bit, as before, we need a probability for all those measurable sets. That's what they're called here. Probability in general is a measure. Measure just means it's a function that maps sets to real numbers. And that also has some same properties as above in a way. But here it's only defined on this subset of sets. The solution for the real line is the Lebesgue measure, where you assign an interval its length, so the distance between the endpoints. And everything else, all the other sets in the Borel sigma algebra you can generate from these operations, you can also express their probability using these operations. One property here is that if you have a disjoint set of events, it could be infinite, but countably infinite only, then the probability of their union has to be the sum of the probabilities. That's for disjoint sets. Okay, is that questions up to this point so far? I mean, that's just the most abstract definition. It's a bit hard to show in a concise way why this is needed. I'll show you the example where we need more general probability spaces soon. Then based on that, a bunch of terminology. This will be repetition for sure. We have events. Events are just any of these sets that we can assign a probability to. They're called measurable sets in general. And this is just the requirement that we want something that we can assign a probability to. And straight from the properties, because we required them, this is all straightforward to show. We define the complement of an event as just the event that this event, the first event, does not happen, and that has the inverse probability. If we take the union of events that are not necessarily disjoint, then the sum of the probabilities is an upper bound. This is called the union bound. It basically just follows from the definition of sigma algebras, but it's a very useful tool in analyzing algorithms, because here you have virtually no requirements about these sets. They can be arbitrary, they can overlap, the events can be dependent and everything, but we can still upper bound their probability. So we'll often use this to bound in an algorithm that something bad happens and that there's several ways in how something could go wrong. But if you can just have an upper bound on the sum of the individual probabilities for what everything could go wrong, that's an upper bound for having anything go wrong. Okay, so if we have some events, we can talk about independence, and this is really just defined via their probabilities. Events are independent if the probability is factor. So if you take the intersection that all these events happen at the same time, then that has to be the product of their probabilities. The usefulness of this definition is really that it doesn't need any intuition what independence means. It's a purely algebraic thing. You just check if the probability is factor. I'm not sure if we ever need this for infinite sets of events. I guess we do for sequences. So whenever we talk about an infinite set to be mutually independent, what this means is that every finite subset is independent. The mutually independent is important. There's weaker versions where you just say so here all the k sets together are independent, which means they're the intersection of all the events at the same time has to factor. You could also take, say, pairwise independence, where you only take two out of these elements and check if their intersection is the product of these two probabilities. That's a weaker notion. And you can say, in general, a k-wise independence. The higher the k, the more restrictive. And mutually means k is all of them. That sometimes plays a role. It's just important to not mix those up. But they're really an easy thing. So just again, pairwise independent would mean that for all I and j in our index set, I'm talking about the same events, A1 up to AK here. The probability for AI intersected AJ has to be the product of their two probabilities. But this does not in general imply mutual independence. There's examples, easy examples you can construct. I don't know. Do we need one? There was a cute one with the colors of edges in a triangle. So you color the edges uniformly at random in one or two of two colors, either red or blue. And then you ask whether, I think the vertices. And then you can ask for each of the edges, does it have two different colors at its endpoints? And if you take any two of these edges and you ask, are my endpoints colored in different colors, then these are pairwise independent. But if you take all three of them, they're not mutually independent, because if you know if you know one color, you fix one color arbitrarily, and you know these two, then you know what the color is, and then the third edge is determined. So the events here would be A1, A2, A3. AI is edge has two colors at endpoints. And then among this set A1, A2, A3, it's two-wise independent or pairwise independent, but not mutually. Okay, just a small example to make that point. You've probably seen some examples before. The last bit we can do with events is talk about conditional probabilities. And in the end, this all kind of just boils down to sets and subsets and kind of Venn diagrams. So the probability that A happens, given that we know that B happens, if you think of the events as some subsets, which really is what they are, if you know that B happens, right, then if in general the size of A was its probability, now it only becomes the size of A intersected B versus the overall size of B. And that's exactly what's written here, right? I guess I could all of B. And of course, we have a problem here. If the probability for this event B is 0, conditioning on B happening sounds like a bad idea. It's algebraically certainly a problem, but also intuitively, if you think about this, you're betting on B to happen, and then you talk about how likely is it that A happens. If B has probability 0, this shouldn't make sense. Now, this is easier said than done. It sometimes could look very promising to condition on something, and then you find out it has measure 0, which is not always obvious. In the discrete case, it's obvious. In continuous cases, it sometimes isn't. Okay, last bit is the law of total probability. Is just a way of reformulating the definition, but it's often useful as a tool to compute things. If you want the probability for some event A, you can rewrite that as conditional probabilities involving some other events. Now, it's important that these other events form a partition of the entire space. And then the proof of this equation is completely boring. You just plug in the definition. But it's useful to think about it as a kind of case distinction. And whenever these conditional probabilities are easier to compute or evaluate, the law of total probability can help determine or compute things. Okay, last very important terminology, maybe not the last term, are random variables. So far we have set up the general universe, probability spaces. What are the things that we can sensibly assign probabilities to without running into paradoxes? And we've defined events, which are really the things that we can assign probabilities to. Things really get interesting once you talk about random variables, which are functions mapping these elementary events to some other universe. It could be anything. Oftentimes we think of it as numbers so that we can compute with these. And remember, I said earlier in our toy example here, for the die, this omega was just some more symbolic set. So if you define it like this, then you couldn't sensibly talk about say adding up two dies But of course, we could map all those to numbers. So we could have x is the mapping to 1 to 6. In the natural way, you just count the dots. What did I do? And that way you can talk about the numerical value. Okay. So boring example of a random variable. Think of it as a random variable can throw away information, and then it can become a more versatile tool. It could say, we could also have y, which maps this just to even and odd in the usual way. That's another random variable, not mapping to the real numbers, but yeah. We'll see many examples where this will become clear. Now we have a new type of event, namely that a random variable has a certain value. With the obvious definition, it's the set of all primitive events that map to the right value. And we can define, so this was going from a random variable to an event. We can also go the other way around, from an event to a specific random variable, which is the indicator, just saying yes or no, 0 or 1, does this event happen or not? So again, this is this Iverson bracket, which is 1 if the event happens, if omega is in A, and 0 otherwise. Okay. Then we can define a few terms. Most of these you'll have seen. So if you have a random variable x, and this is some real number here, or at least something where it makes sense to talk about less or equal, you can define a cumulative distribution function as just the probability that this is below a certain value. If x is discrete, then necessarily also the range you map to will be discrete. For a continuous random variable where you start with something that's not discrete, you could map it to something discrete, or you could map it to something continuous. And if you map it to right, okay, that's still for the discrete case. You can define the probability mass function. It's just for all the values in your universe here. Suppose that's discrete. So if say that calligraphic x, that's an h, is the natural numbers, then you could define something like this. Just the probability to have a certain value, and that completely describes the probability distribution, the random distribution. If you have some continuous random variable, you can still define this cumulative distribution function. And it's often useful if this is smooth enough to look at the derivative instead. And the derivative of the cumulative distribution function, if it exists, is the probability density function. That's again things you'll have seen. The standard way to deal with most continuous random variables. And a slightly non-standard piece of notation is this equals with a d above it, which I'll use to denote that the two random variables on the sides of the equality have the same distribution. Formally, it just means that their CDFs are the same. There's many ways people use notation for the same thing. I think it turns out to be very convenient if you combine random variables. Now you can say x is equal in distribution to y plus z. And if these are mapping to real numbers, it's clear what that means. But it's a fairly sophisticated, if you express this via the distribution function, you're already talking about some convolutions and so on. It's a nice way to express what we want here, equality in distribution, without requiring special notation for standard operations. All right, we've talked about independence for events. You can also talk about independence for random variables. And the way to think about this is random variables here, they can map to any kind of set X. Often we'll think of that as real numbers, but it could also be multidimensional. It could be mapping to R to the K. And then we can, for this vector X, the vector random variable, we'll just call these functions that we just defined the cumulative distribution function, or the probability mass function, or the probability density function. We call those the joint versions. And we can look at individual components of the vector and then look at the marginal distribution of that, or the marginal functions. And now a set of random variables, or a collection of random variables, is independent if they're joint distribution, they're PDF or they're PMF factors. For example, X and Y are independent if the probability that they together have the certain values, so X, capital X is the random X is equal to X, random Y is equal to some Y, that has to factor into the probabilities of the two events. It seems like it's the same thing as for events, but I guess formally it isn't, but it naturally follows. And this is, I guess, for discrete, you can do the same for the probability density function, and it does the right thing. Okay, here's an important bit. That's what we'll come back to many times. IID sequences of random variables. IID stands for independent and identically distributed, and the independent stands for mutually independent. Nobody says that, but it's implicitly there. So this is often the starting point of some theorem. You have an IID sequence of random variables. Maybe they're all fair coin tosses, so heads or tails, or 0 or 1. But you have an infinite, countably infinite number of those, and then you can work on from those. So that's just what that formally means. Okay, I guess I lied earlier. This is another important term, the expected values. But you'll have seen about this. If you have some random variable, you can take its expectation. And for this, really, you need to be able to map. This only works if you map to some number or something where you can compute, because here you're taking sums of values that X can take. Of course, the definition of expected value of X is the sum of all possible values times their probability, if that's the discrete case. If you have a density, then you take the integral. It looks very similar to the sum case. I guess it's nice here. Shows the analogy. You can also define this in general set measure theoretic terms, where now the integral becomes a Lebesgue integral. We won't actually need that, so I think we don't need to talk about it. It could happen that a random variable does not have an expectation. Whenever that sum or integral doesn't converge, then it just doesn't have a random, well-defined expectation. That can happen. Okay. Important properties of the expectation are just following from the definition. Remember that it is a sum or an integral, and these are linear. So if you scale a random variable by multiplying its outcome by a constant factor, the same will happen to the expectation. If you add up two random variables, the expectation of the sum is the sum of the expectations. You know this, but it's good to keep in mind. And as an important special case, if two random variables are independent, then their expectations factor. This again follows directly from the definition, but you need to do the math, I guess, to see it. if you can factor their probabilities, then you can split away the sums, and it becomes the product of two sums. Note that here this doesn't imply the other direction necessarily. Don't know if there's a nice. There's certainly an example, but not one I can come up with now. Conditional expectations are a slight twist on what we had before. It's essentially the same thing. You just take, whenever you had probabilities before, you now take conditional probabilities. Yeah, conditional expectation for an event, I think this there's an x missing here, right? Should be multiplied by x. More important is the conditional expectation, where you have take the expectation of some random variable, and the event that you condition on is another random variable having a certain value. This often pops up, so it's worth mentioning as a special case here. And if x and y are discrete, the obvious definition works. Just replace the probability for x having a certain value by this conditional probability. If x and y are continuous, then in general you have to be careful with these kind of statements, because you're conditioning on an event of probability 0. If you have a continuous random variable, that the probability that it takes one specific value, the measure of a point set, is usually 0. But you can still sometimes define things via densities. So if you have two continuous random variables, x and y, with a adjoint density function, then you can define the marginal density of y by integrating x out. So just what it says here, you take the joint one, you integrate over the entire domain of x, but you keep y as a variable. And then you can define this conditional expectation properly using this marginal density. If you just go from the definition up here, you would be conditioning on an event of probability 0. And so this would not work. But if you have densities, you can give a sensible definition to this conditional expectation here. The last thing I want to point out here is if you have some conditional expectation of either kind, discrete or continuous, you can actually turn that into a new random variable itself. So first of all, if you fix the value of y, the little y, you fix the value that you condition the random y to have, then that's a function. And now you could say I'm taking one random variable, I'm applying a function. That's just composing two functions. That's again a random variable, g of random y. And so we can denote this by this. But this notation, as widespread as it is, you should keep in mind it really stands for one of these two things. And for example, if x and y are continuous, but they don't have a nice density, it might not make sense to write this. Could be not well defined. But if it's well defined, you can use the law of total expectation, which is expressing some expected value by averaging over y and then inside taking the conditional expectation. That's one of my favorite tools, because sometimes you can evaluate a hard to compute expectation by first conditioning. It's a bit similar to the law of total probability. That can be a powerful tool. All right. Pinky promise, last slide on this, some famous distributions. There's no esoteric ones, you'll know those. I just wanted to have the notation somewhere written. So just a B with P will be the Bernoulli distribution. It's a biased coin flip, where P is the probability for having a 1, and otherwise it's 0. Then we have the binomial distribution, which is the sum of n such coin flips, where n and p are parameters. Then we can have the discrete uniform distribution. That's what the die was. So our random die, again, the random die has uniform distribution between 1 and 6 in the obvious way. Let me just write this sloppily like this. Another thing that pops up is the geometric distribution, which is you have some coin with a probability p of coming up as a 1, and you have now you count, you keep flipping until it shows a 1, and the number of coin flips you needed in total is the geometric distribution. Okay, the only continuous distribution that I'm using for sure is the uniform distribution. For example, over the unit interval. There's of course many others, but I don't think we need any of them. All right, let's do a short break. Start again at 11. I should probably have put a Slido question about half of this and check if you even need to go through this. I tried to run through it fairly quickly, but it still took a bit of time. Was it useful at all, or? I guess you know this, but maybe a refresher is useful. Never hurts. I think last time I did this, I swapped the order and first gave the motivation why we need some of the more abstract probability spaces, and then did the formal stuff afterwards. And that felt, that was very annoying to do, because half the time I was forward referencing stuff. So instead I swapped it, but now there's a long section where it's not clear why we have to do this. Goody, shall we move on? Back to computation. In the next section, we'll study some formal models for what computation with randomness could mean. And I just want to set the stage solidly for talking about what running time here is. And you'll see it's not actually a problem in the end, but to capture the full possibility of what could happen, I think is useful to start general. As before, we'll think of a minimalistic model of computation, Turing machines again. The formal definition was in Unit 2, if you want to look up the details. Here we add a little bit to this Turing machine. So again, Turing machine, it has some states. It has an input alphabet, which is the initial things written on the input tape. A superset of that is the set of all symbols I can write on the tape. Then I have the transition function. That's the program, the most important bit. I have an initial state. I have some blank symbols that the tape is filled with if I haven't touched it yet. And I have a specific state where I terminate if I ever reach this. Now, a probabilistic Turing machine is that same thing, and it's a deterministic Turing machine, which maybe is worth stressing, where we additionally have another read-only tape, which is conceptually filled with random bits. So it's an additional tape. So the machine has two heads. We've talked about multi-tape Turing machines very briefly in Unit 2, or at least it's on the slides. In general, you can define Turing machines with several tapes, and you can show that you can simulate everything on one tape with a bit of a blow up in space, blow up in time, I guess, and space, but time is more affected. So here again, we do the same. So think of your Turing machine with the states here. There's the infinite tape for the input. Oh, this keeps... Oh. There's some weird operation I do, and then it loses focus in the window and doesn't come back until I'm on the keyboard. So that's the input and output tape, which you can read and write. And then there's the random tape. Where you can still move your head back and forth, but you can only read. There's no writing facility. Now, I guess you can imagine how this would be formally defined. The key thing that changes is the transition function. The input now is not just a state currently of the current position, and so I didn't finish drawing the read-write heads, I guess. So there's the read-write head here. I can move left and right. And there's the random bit read-write head. But this can only read things. So it's not a read-write head, it's just a read head. So the transition function, what the machine can do is it can take this symbol and it can take the symbol on the random tape as an input. Previously, it only had the state and the symbol on the tape. Now we have an additional symbol, random bit, R. And the next state, as before, is a new state for the internal memory. It's a new tape symbol I write on the input-output tape, could be the same as A. It's a head movement for the input-output tape, and a head movement on the random tape, but no written symbol because it's a read-only tape. Okay, so far so good. In particular, the whole machine is supposed to be deterministic. Once you fix the random bits, there's nothing further random. All the randomness or all the non-determinism comes from those random bits. If you fix what's in the red tape, then the rest is determined. We'll eventually get to the point that we say this tape is filled with random coin flips or bits that are chosen from this Bernoulli 1/2 distribution. And well, there's your IID, mutually independent, all identically distributed. So to define what computation is, we go through the same steps as in Unit 2, but I compressed them a lot. Back then, we had the configuration of a Turing machine, which was just a concise way to write what's on the tape and what the current state of the machine is, and where the tape head is. And that's all we needed to know. So the compressed way to store that was this alpha q beta, where your tape symbol contains alpha beta concatenated. Q is your state, and the position of Q within alpha beta indicated where the head is. And if I remember correctly, it was on the first symbol of beta. Okay. Now we have a second tape, so we have a second component in the configuration. It's just a pair of those things. And the second component works exactly the same, except that now these rho and sigma together are the content of this, the red tape, of the random bit tape. Okay. Then we can define this computation relation, where it really is a function here because it's deterministic, in almost the same way as we had back then. You follow the transition function. The configuration uniquely determines the state you're in, what you read as symbols. So you know what the output will be. Then you replace the state with the new state. You move the heads if needed. And maybe you replace a symbol here if you write a new symbol, just as we had it back then. And based on that, we can define what is the function computed by a Turing machine. And so the difference here is that the actual input is just some string x, and we have some random bits to somehow decide. And for now, let's say if we fix the random bits rho as part of the input, I can write m of x and rho, the random bits are given, is a certain value y, exactly when from the initial configuration, I can reach the terminating condition where I reach this halting state, and I've produced y on the input-output tape. This is almost the same as before, except that I have this second component, but for the function computed, I'm kind of ignoring it. I just say there's something will happen to the random bits, but I don't actually care. These are just defining what the steps in between are. But this is deterministic, okay? Important. If I fix the random bits rho, everything is predetermined, and the machine, depending on how it's programmed, either it can reach a halting state or it may not. It might be broken, but this will be one well-defined sequence of steps. And if it reaches some configuration, it reaches uniquely only this one. And so y is well-defined. It's either not terminating, then there's no value, or it's a single value. Okay, many words for saying deterministic. Of course, now we don't want to fix the random bits. They're not part of the input. These are randomized machines. So the randomized computation will become a random variable. I'm essentially now taking this function m computed by the machine. I keep the input, but rho is now formed by random variables, namely by these IID Bernoulli 1/2 random variables. Okay. And so now this computation, or this function computed by the Turing machine, has become a random variable. And we can talk about probabilities for computations. For example, the probability that the machine computes a certain output y is the probability over well, all the bits that make it output y. So far, so good. In principle, now a randomized Turing machine could have different outputs, right? It doesn't need to compute the same value y. It could compute different values y, and it could also sometimes not terminate. Of course, from a programmer's perspective, what we really want is a machine that outputs the right thing with at least a good probability, but we'll come back to that a bit later. For the moment, this, I think, is very natural, but there's a big caveat here in that there was a lot of cheating involved in all those definitions. And the first cheat the cheat becomes obvious at this point down here, where I said we put in these random variables, and sometimes the machine doesn't terminate, which means it might need an infinite amount of random variables. So how am I even going to write down the configuration? So all of this is getting a bit more tricky, just because of this possibility that the machine keeps asking for more bits. But then why would it do that? Like, can't we just restrict it to cases where we never use infinitely many random bits? Why would you? It sounds completely stupid. In particular, we had this in Unit 2 as well. We said in general, Turing machines, if you give me some arbitrary program, they might do all sorts of nonsense. But for the discussion of P versus NP and all that, we restrict to total machines that always terminate after a fixed amount of time. And you can always convert. If a machine would be running for longer, you keep a timer, and when its time is up, you just shut it down. Now, for randomized Turing machines, for probabilistic Turing machines, there are some simple tasks that seem not to work with that, and so we don't want to disallow these infinite computations. And here's a simple example. Again, I'm sure people will have seen random rejection sampling, but let me go through this slowly, and you'll revisit it in the tutorials just to make extra sure. So the way we define things is everything that we have that is random are random bits, and they are uniformly random bits. Now, suppose we want to simulate a six-sided die, a uniform six-sided die. How can we do that? I mean, I could start with, okay, I'm flipping one bit and ask, is the number odd or even? And then I've nicely divided things up. So I have three options left. Is it, say, if it's odd, is this 1, 3, or 5? How do I do that with just bits? Seems tricky, but luckily there's a general solution that always works and is a lovely algorithm, which is called rejection sampling. So for this concrete example, it's spelled out here. I just called it roll die. The function will refer back to that a few times. It keeps looping it does this as a potentially infinite loop. You draw 3 random bits. That gives you 8 possible answers. You take this as a representation of a number between 0 and 7. And then if it's out of bounds, the die should have a number between 1 and 6. If it's out of bounds, which means here it's 0 or 7, then you discard this, you reject that random outcome, and you just try again. Whereas if it is between 1 and 6, then you output that number. Okay? Have you seen this before? Rejection sampling as an idea? It's a general trick. If you have something that's hard to sample from, you sample from a superset and then check, have you hit the set you wanted to sample from? And if not, you just try again. And the beauty of it is that it is very easy to show that it is perfectly uniform. Whenever you return something, it has to be perfectly uniform because you gave all the outcomes 1 to 6 exactly the same probability, namely 1 out of 8. Now, the downside, of course, is it might never terminate if you're constantly unlucky. If your random bits are always 0, then this algorithm never returns. Now, of course, you also know, if you've seen rejection sampling, if you do this in practice, it never causes problems, at least in this algorithm, because the expected running time is constant. So to prove that, you can compute what is the probability of doing another iteration of the loop. And here, the probability to leave the loop is 6 out of 8 options. So in 75% of the cases, we're done after 1 iteration. And in 75% of the remaining 25 cases, we're done after 2 iterations. And so you see where this is going. So the number of iterations, I didn't put this on the slide for some reason, is a geometric distribution. And the number of, so success means 3/4. That is, I'm doing exactly the same as if I was flipping a biased coin, where with probability 75%, I'm immediately successful. And otherwise, I keep trying and I count how many tries did I need. So that's exactly the geometric definition, geometric distribution by definition. And then you could either look up, we know the expected, oh, this is annoying. The expected value of the geometric distribution is just 1/p. That's worth keeping in mind, but of course you can prove it using the series that is on the slide. Sorry, p, here it's 1/p. And the proof is just this sum. That's by definition that's the definition of the expected value. So this algorithm is correct. It uniformly samples. Its running time is a bit wonky. It sometimes takes longer and sometimes takes shorter. But it's well characterized. We can understand how long it takes. It's a random variable that's well understood. And it has a small expectation. So after a constant amount of time or constant amount of iterations, you'll have your output. So why did we talk about this? I mean, number one, it's a beautiful algorithm worth knowing. Rejection sampling is a beautiful idea. But it also shows you if you were to try this sampling in a different way without this kind of infinite loop, it seems really hard to do. And so we seem to want to deal with infinite runs in this context. Question? So the question is, can you use arithmetic coding for this? I think you'll end up with the same problem. Yeah, think about it. I mean, you could essentially turn, if you want to sample from a more complicated distribution, or maybe even a sequence of things, then arithmetic coding is a good way to turn to generate a sampler that is efficient in terms of the number of bits that it uses, but you can't avoid this case that you have to keep going with arithmetic coding. The nice thing is you'll prove in the tutorials that it's not possible. So it's not a hard proof if you look at it from the right way. For here, I'll just leave it with the statement that we seem to want to keep infinitely running or potentially infinitely running probabilistic Turing machines because they have practical use cases. Again, you'll look at this a bit more in detail in the tutorials, and this is only one example. So what does that mean for our definitions? What could possibly go wrong, right? Number one, if you have a randomized Turing machine, it could still do the same nonsense as before. You could enter an infinite loop, even if that doesn't consume more random bits. Okay, but that type of problem we can actually discuss away. That's the same as before, and we can keep a counter, or there's ways to deal with this. But there's a new problem that didn't occur before, which is what we used in this roll die. We have branches in the code, and these are based on random bits. And there is a possibility to be constantly unlucky. Like in the case of roll die, always take zeros. So formally, you could say for every time t that you put your timer on, there's a certain probability, non-zero, that you need more than that many steps. And the computation is doing something sensible there. It's a new thing that didn't happen for deterministic Turing machines before. It did happen, though, for non-deterministic Turing machines. And the formal definition there is just said, OK, the running time then is infinite. If there's an option non-deterministically to keep going forever, then that should be infinite time. OK, so we'll probably have to keep that. But now, like for our algorithm roll die, is that a problem or isn't it? And also, can we define the expected running time here? Like it seems the expected number of loops was not a problem, but can we define properly what the expected running time of our Turing machine model is in the presence of these weird cases where it keeps running forever? Well, the answer is of course yes, but that's the reason why I introduced some of the abstract probability spaces terminology. You can properly define it, and here's one way to do it. The key question is what probability space do we need? It seems if you start with random bits and everything's finite, oh, everything's lovely discrete. Yeah, but if things are infinitely long, not so quick. So if you had finite bit strings, then that's discrete, even if they're infinitely many. What we really need here is an omega language, I mean, I wrote this here. I'll write this here in the way formal language people would write it. 0, 1 to the omega means it's technically as a function that maps the natural numbers to 0, 1s. That's one string. If you if you think about finite strings, you could say a finite string is what? Well, it's mapping the numbers 0 up to some number to elements in the alphabet. That's a string. And so the generalization is, well, I'm doing the same, but it's an infinite domain. I'm mapping all of the natural numbers to a bit. That's an omega word. So this 1b is called an omega word. Okay, I have to be a bit clearer. That's omega and that's w. And then I can talk about these in the same way. And you can talk about regular omega languages in the same way you do regular expressions for finite languages. There's some cute automata theory in there, but we won't need that. You could also think of these as infinite, as real numbers between 0 and 1, written as infinite binary fractions. So in particular, this is actually a bijection. You can take your infinite omega word and just write 0 dot and then the digits, the bits. And that's a number between 0 and 1. And you can exactly represent all real numbers that way. Okay. It's kind of almost by definition, so maybe it's not super exciting. Bijection? I'm not sure. Like maybe the problem is there's potentially several representations for the same real number. 0.011111 is the same as 0.10 100. So maybe take this. I don't want to lie. So maybe bijection is pushing it too far. Because these are, as real numbers, these are the same. But as omega strings, they're different. Cool. So maybe that's the reason why we don't directly go to real numbers. As a computation, these might trigger different computations. They're different bits. Okay, so morally, you can think about them as kind of real numbers, but just the representations as infinite representations. Clearly, you see that it's a continuum, right? These are at least as big as the real numbers between 0 and 1. So you can't, they're certainly not discrete, but they might be a bit bigger. So also for our configuration of the Turing machines, formally, let's just write that the sigma here, so the remaining part, the right part on the infinite tape, let's say that's an omega word. So we're on the safe side. If the machine needs more bits, there's always going to be more bits because it's infinite. It's a bit annoying that we can't write down a configuration anymore because it's infinitely big. But let's ignore that. It's not a big problem, really. We don't write them down. What we need now is a proper probability space for these infinite bit strings, because that's what we want to take expectations over and compute probabilities from. And it turns out that's a known thing. It's known as the Bernoulli probability space. And as for the Borel sigma algebra for real numbers, where you had open intervals as the kind of minimal elements, here you have, I don't know, the sometimes called cylinder sets, but I guess it's just a prefix. So the pi x are just all the infinite 0, 1 strings that start with a certain prefix x. You can think of it as kind of a restricted way to represent intervals in the real numbers. For real number intervals, you can have an arbitrary start and end point. These numbers here are, in a way, always dyadic intervals. They start at a negative power of 2 and have a length negative power of 2. Right? If you say this set is all the real numbers, it corresponds to real numbers between 0x 0x1 up to whatever xn, and then zeros all the way up to 0, then the same x's, and then all ones. Right? Formally, pi x is just a set of omega strings. And it's all those omega strings that start with a given finite prefix. So important here is that, I should have made that in red. The prefix has to be a finite prefix. And it turns out you can turn this into a sigma algebra by taking the closure under these operations. So you take all those pi x sets, and you take countable unions and complements, and that is a well-defined sigma algebra, the Bernoulli sigma algebra. So that's the measurable sets we can talk about. Okay, these pi x's, unions, and complements thereof. And what's the probability? You can assign the measure of 1 pi x. And it's very natural, I think, that you say, if we've seen a certain prefix of a certain length, I've seen n random bits, so it should be 2 to the minus n as the probability to see exactly that string. And the rest is, I don't know what comes after. I'm summing over all of them. And so you only fix the probability, only fixes the prefix. So this defines the probability for the generators. And the probability for any other set you can derive from that and using the abstract properties. And you'll do that in the tutorials to practice it. Okay. Maybe let me briefly sketch how this could look like. If you go back to our roll die example, what are the kind of bit strings where it terminates? It always chooses 3 bits at a time. And all of these, as I'm drawing here, are numbers between 1 and 6. That's 6, right? Yeah. So in all of these cases, we're done. In these 2 cases, we continue. So you have to zoom in here. Then you do the same 8 cases. So we have 0, 0, 0, and then 0, 0, 0, 0, 0, 0, 1, 1, 1, and all the other options, 0, 1, 1, etc. Here we terminate again. For these 2, we have to continue. And this, of course, gives you some large tree. What's the probability that this guy terminates? Well, it's the measure of all, it's P of, I guess I want to, can I sum here? I guess it technically is closer to an integral. Let's integrate over all rho. Do I have a, yeah, 0, 1 omega, I guess is the closest. Oh, not again. This is some super annoying. This one's also frozen, so that's not a good sign. Well, you would want to go over all these infinites, the omega words rho where the algorithm terminates, and sum up their measure. Dude. This seems to be properly dead now. I'll try for a minute to get the live stream back running. If it doesn't work, then maybe just give up there. Excellent connection. Okay. Seems it's running again. Good. Let's pretend it works. I lost some of the drawings, but I guess we'll have to keep the good memories of them. Let me not repeat the drawings, maybe. The point was you can define a language of omega strings. So the roll die example. The roll die terminates if and only if the initial bit string we start with is in some language T, which is a subset of these omega languages. And we can now, with this Bernoulli probability space, we can talk about what's the measure of that set T. And you can re-express that using these prefixes. And the prefixes nicely turn into the cases where the algorithm terminates. I think this is doable enough, but it's worth that you do it actively in the tutorials, just to kind of be forced to mess around with the definitions a little bit. We won't much use that formal, like this probability space and how to work with it. We won't need it much, but I think I always felt it was very unsatisfying that you talk about these randomized algorithms, and technically many things were not well defined. The expectations, you always needed hand-wavy bits to define what they mean. So with this setup, which is not too complicated to work with, as you'll see, you can do this properly. And the benefit is, for the probabilistic Turing machines, we can pretend that there's no randomness. The randomness is upfront. You decide once for this infinite omega word of bits, and then the machine can be deterministic, and everything can be computed based on that. The last bit for this to finish off is generalize what is running time for our new notion of Turing machines. And we can define the worst case time as before. So the time the machine takes on a given input is the supremum of the time steps over all computations The original Unit 2 slides had an infimum there, which is nonsense. It has to be the worst case, so the largest. And it's supremum instead of maximum because it could be infinity. It could be infinity at the time. But we had the very same definition for non-deterministic Turing machines. There it was also possible that some branches of the possible computations just keep running forever. So time without a qualifier is the worst case time on that input. Right? Time is worst case. And that's not always very helpful. For the roll die problem, it would be infinite. And so time roll die on any input. It doesn't have an input actually, right? It's just spitting out some random. It would be infinite. Oh, not again. I don't know what this is. It needs to be solved. This is super annoying. It happens way too often. Some new nonsense. Yeah, have an idea. Maybe not now. Okay, so here the worst case time is infinite. But we can define an expected time now that we have a probability space at hand, and that's just the expected value of this. And here's a last bit of notation we'll sometimes use. I write in the subscript of the expected value operator the random thing that we take the expectation over. This doesn't technically add anything. It's just for clarity of the presentation. This is stressing that the random thing we're talking about here is the random bits. Everything else is deterministic. And then formally, you can say the expected time, what we take expectation over is the smallest number of time steps t that it takes from the initial configuration to reach the halting configuration. If you start on a specific random row, that's the random bit. Okay? In red, this is the random part. And then, of course, also the t is a random thing because it depends on row. So the whole thing is the whole infimum is random. The shortest number of steps to reach the halting state for a specific sequence of bits. And the expectation over that, over all the bits, that gives you the expected running time of this probabilistic Turing machine. As before, we define, instead of a specific input, an input size, you just take the worst case of all inputs of that size. That's as before. So I try to be consistent with having lowercase time to be on a specific input and uppercase time, the worst case over inputs of a given size. Of course, instead of the expectation, you could also take the full distribution, and sometimes we will. But what's useful here for starters is the expected time is finite if and only if the probability to never terminate is 0 exactly. In other words, we almost surely terminate if the expectation is finite. And that's pretty much what a sensible algorithm should do. It's okay if there is a hypothetical option for it to run forever, as long as it actually never does so with any positive probability. You will remember from probability theory that this almost surely, something that happens with probability 1 is not so intuitive. You can upfront fix some event that had probability 0, but it can still happen. In hindsight, you know. But we won't see it happen for our roll die algorithm. Just for the notation, I mean, for the formal definition is not so important. Instead of time, you could also look at how many random bits did you need. That might be a useful thing to look at. You can formally define it by how far into the infinite row did you ever move. And here's a way to formalize that. But the intuition is just how many random bits did you use. Again, you can define this as the worst possible. Again, if you fix just the actual input, it's a random thing. So it's the random number of random bits that you used. And the small case random is the worst overall possible random bit strings. Again, could be infinite. So oftentimes we'll talk about the expected number of random bits that we used. And that's a bit of a mind twist, that the cost of random bits is also random, but it's not such a bad thing if you think about it. I mean, it's not so unintuitive. You just consume this special operation, bit ein bit, give me another bit, a certain number of times, and how often might depend on the previous bits. Nothing more surprising than for the running time. But we'll use this occasionally. For some algorithms, it's important to economize on the random bits as well. Yeah, looks like a good place to stop. Which also means we haven't done any actual algorithms, but we'll very soon come to that. What it means to solve a problem with such a machine is the next thing we'll look at. That's very brief, and then we'll dive into actual problems, actual algorithms. But not this week.